In this section, your book covers the enthalpy of formation. Let's define that. Enthalpy of formation is a heat exchanged when 1 mole of a compound is formed from its elements at 1 atmosphere of pressure. So what do we mean by formed from its elements at 1 atmosphere of pressure? Well, the 1 atmosphere is clear. Let's use an example to show what we mean by formed from its elements. Take this reaction, which shows the production of CO2. Carbon solid, usually carbon graphite is what this represents, is the stable form of carbon at 1 atmosphere pressure under normal conditions. So this is the elemental form of the stable elemental form of carbon. O2 gas is the stable elemental form of oxygen. It's the form of oxygen that is in the air all the time. So what we're showing in this reaction is the formation of carbon dioxide gas from its elements as they are found under sort of normal conditions of temperature and 1 atmosphere pressure. Let's take another example that represents the stable form of elements at 25 degrees and 1 atmosphere pressure forming some compound. So, for example, calcium chloride solid. So, how do we represent the formation of calcium chloride solid from its elements? Well, the stable form of the metal calcium is simply written as calcium solid. So this is like metallic calcium. And pure metallic calcium is going to be a solid at 25 degrees Celsius and 1 atmosphere pressure. Chlorine at 1 atmosphere and 25 degrees would be Cl2 gas, and that is the pure stable form of chlorine under those conditions. Now, the formation shown here is already balanced. Calcium solid plus Cl2 gas forms calcium chloride solid, and we don't have to do anything else to balance this equation. But this represents the formation of calcium chloride from its elements, calcium and chlorine. Now, as you can tell, you're going to need to remember what are the stable form of the elements in the periodic table at 25 degrees and 1 atmosphere pressure, the pure form of those elements. Most of the metals we write simply as we did with calcium solid. So iron, copper, lithium, beryllium, all the metals on the left side of the periodic table, generally we represent just as the metal found in the solid state, the exception being mercury, of course, which is a liquid. So the stable form of mercury at 25 degrees and 1 atmosphere pressure would be HgL for liquid. Let's do another example. Formation of sulfur hexafluoride gas. So in order to represent the formation of this from its elements, we need to know what are the stable forms of sulfur and fluorine at 25 degrees Celsius and 1 atmosphere pressure. Well, sulfur is simply represented as solid S, and then the S in parentheses to represent that it's in the solid state. Fluorine is a gas, a diatomic gas, F2, and so we'll write that as F2 gas. Then again, I knew from just common experience, and you can find out from looking in your textbook, what is the form of fluorine at 25 degrees and 1 atmosphere pressure. You'll find that most of the halogens are diatomics. Fluorine and chlorine are diatomic gases, and bromine is a liquid, diatomic liquid, and then iodine is also diatomic, but it's a solid, and so that's how you'd represent those in equations like these. Now we're not done with this particular one, because you'll notice that on the right hand side we have 6 fluorine atoms, and on the left hand side in the reactants we only have 2 fluorine atoms, so we're going to have to balance this by putting a 3 in front of the fluorine. And so now we've written out the formation of sulfur hexafluoride from its elements at 25 degrees and 1 atmosphere pressure. Let's do one more. Formation of dinitrogen oxide gas. So what are the stable forms of nitrogen and oxygen at 25 degrees and 1 atmosphere pressure? What are the common forms of those elements? You might know already. Nitrogen, just in the air, what is it? Well, it's N2 gas, right? And the stable form of oxygen is O2 gas. So these are the pure forms of those elements. Now notice that this equation is also not quite balanced. We have 2 oxygens on the left and only 1 on the right. However, remember that our definition is 1 mole of a compound formed from its elements at 1 atmosphere pressure. So we can't do anything to the right-hand side. We have to leave that as 1 N2O, which means we're going to have to balance this equation by using a fraction, putting 1/2 in front of the O2. And so now we have a balanced equation representing the formation of N2O from its elements. Now, what is the heat exchange and how do we determine that? Well, for many reactions, we can simply determine the heat exchange for the reaction simply by measurement. So we do an experiment, for instance, the combustion of carbon in presence of O2 to form CO2 has a delta H reaction of minus 393.5 kilojoules per mole. Calcium chloride reacts with chlorine and we can measure its enthalpy to be minus 794.6 kilojoules per mole. So again, an exothermic process. So in these particular cases, you can simply do the reaction and measure the enthalpy exchange for the reactions. Now, how is this then related to the actual the enthalpy of formation for the compounds like CO2? Well, we are going to define the enthalpy of formation of the pure elements like carbon solid and oxygen, diatomic oxygen, as 0. And thus, the enthalpy of the reaction is equal to the enthalpy of formation of CO2, because since the elements themselves have enthalpy of formation of 0, then the enthalpy of formation of CO2 is simply equal to the enthalpy of the reaction. And so the enthalpy of formation is minus 393.5 kilojoules per mole. Furthermore, then the enthalpy of formation for calcium chloride is minus 794.6 because the pure elements, calcium and chlorine, are defined as 0. And that'll be the case for all the pure elements. The enthalpy of formation of all the pure elements are designated as 0. And this gives us a starting point for defining the enthalpy of formation for all the other compounds, like CO2 and calcium chloride and SF6 and N2O. So why is this useful? Why do we want to know the enthalpy of formation for these different elements? Well, one reason that they're useful is that we have now, from these different reactions that we run, we have whole tables defining the enthalpy of formation of different compounds. For instance, you see up in this table, the first one on the list is aluminum chloride, a solid, AlCl3, and it has an enthalpy of formation of minus 705.63, and you can see there's lots of ones that I've represented just a small portion in this table right here. How are we going to use these? Well, using the enthalpy of formation values, we can predict the enthalpy of reactions for which we can't easily determined by experiment. So if we have a reaction and we don't know it's the enthalpy of the reaction and we can't easily determine it by experiment, we can use the following relationship in which the enthalpy of the reaction is equal to the sum of the enthalpy of formation of the products minus the enthalpy of formation of the reactants. And we'll talk a little bit later about where this equation comes from and why it works, but for now we're just going to learn how to use it and the enthalpy of formation of different compounds to determine the enthalpy of a reaction. So just to further clarify, the N and the M in this equation represent the coefficients in a balanced reaction. So the coefficients in front of the reactants and the products. If we have a reaction like the combustion of C2H6 and oxygen to form CO2 and water, and this is balanced, then we can calculate the enthalpy of this reaction from the enthalpy of formation of the reactants and products. So let's see how this works. So our enthalpy of reaction is going to be equal to, we're going to take 4 times the enthalpy of formation of the CO2. Now look up in your table and you'll see that, let's go back just a little bit here. There we go. You'll see that up in the table we have that the enthalpy for the formation of CO2, carbon dioxide, is minus 393.5, and we have 4 CO2 molecules produced in the reaction, so N is going to be 4 in this case. So 4 times minus 393.5 plus the enthalpy of formation for water, for which N is 6, if you look in the table, is minus 285.8. Okay, so that's the product side. We're going to sum those and then subtract from that the enthalpy of formation of the reactants. In this case, we have 2 moles of C2H6, and we see up in our table, if we look at C2H6, it has an enthalpy of formation of minus 83.85. So that's ethane gas, C2H6. We have 2 moles of that, so it'll be 2 times minus 83.85 kilojoules per mole. And then finally we have 7 moles of O2 in our reactants. So that'll be 7 times the enthalpy of formation of O2, and of course since it's a pure element, we know that its enthalpy of formation is defined as 0. Okay, so we're going to sum those for the reactants and subtract them from the enthalpy of formation of the products. So just to reiterate again one more time, we have the 4 moles of CO2 times the enthalpy of formation of CO2, which we find up in the table as 393.5, plus 6 moles, right, of water, which we find to be 285.83 kilojoules per mole. Then we see in the reactant side we have 2 moles, so 2 times minus 83.85 kilojoules per mole, which is the enthalpy of formation of ethane, and then 7 moles of O2, for which the enthalpy of formation is simply 0. Working this out, we find that we have minus 3,289 kilojoules per mole on the product side of this, and minus 167.7 kilojoules per mole on the reactant side. subtracting those through, we get 3,121 kilojoules per mole. That is the enthalpy of the reaction, and we determined it simply from the enthalpy of formation of the substances involved in the reaction.